Hey, how are you?
I'm good. How are you?
Good. Thank you. All right. What's new?
Not much. I mean, we just saw each other yesterday, but I was doing UWorld questions on electricity and magnetism
Huh?
um this morning,
Yep.
and yeah, so I there was a question that was
Mm-hmm.
asking within this about like harmonics and like fundamental frequency. And I was hoping we could review all of that because I was confused.
Yeah.
Yeah, I guess I don't really get it, especially like closed, open pipes and all of this. Yeah.
Got it. Okay. So, yeah, let me open up a whiteboard here. Okay, so this stuff falls in the category of simple harmonic motion. Oops. Okay. Hmm, I'm just writing like that, but okay, so okay, that's better. Okay, so let's talk about what this is. So usually the easiest examples to show would be um so yeah, one could be like a mass on a attached to a spring. So if we had something like this, and this is a mass, and let's say like, you know, down this center over here is its location, I guess. I'll say like this is at time of zero. So what happens is if you pull that mass, like let's say to the right, by a certain distance, let's say by, let's say we're pulling it like over here, the where I wrote this like vertical dotted line. Um, that could be a change in x. And if it's there, so I can redraw this like that. So, and let's say this is like time, like let's say like 1 second or something. Um, when you let go of the mass from this position, the spring will be considered something called a restoring force. It'll restore it back to its equilibrium state. Let's see if I can do this. So let's say like straight down. Here's the equilibrium, and then like, oh, whoops. And straight down there is the other is where you pull it away from equilibrium. What will happen is it will overshoot so as the restoring force pulls it back towards the equilibrium position, it will, because of a momentum, it will overshoot it. So you'll get, like, it'll return to the equilibrium state, but then it'll go like, so maybe I'll just draw that. Back to that equilibrium state, and then it'll be here because it will overshoot it. And after, and then, yeah, this is also delta x. It'll overshoot it, and by that point, it's getting ready to go back to the right to be restored to that equilibrium position, but it'll overshoot it as it goes back to the right. So this is a, a spring mass, let's say, system. Now, let's think about this in terms of potential energy, like elastic potential energy, kinetic energy, and let's say like velocity. So at its original location up top, there's no, like, the elastic potential energy here is really zero because it's not being moved from its equilibrium position. Its kinetic energy is zero because it's not moving, which, means its velocity is zero. But when we pull it to this position here, oh yeah, I'll say like time equals 2 seconds here, time equals 3. So yeah, at this point here, where it's being stretched, it's not moving yet, but it's the amount that it's stretched is causing there to be an elastic potential energy there.
Mhm.
So, and we can say that it's at its maximum point. So I'll say like U max. Its kinetic energy still zero, velocity still zero. And when you let go from that point, it'll start to accelerate, to the left and it'll go past its original equilibrium position. So at t equals 2, wherever it is going to be at its maximum velocity, right? So we can say, yeah, like here, the elastic potential energy could be at a minimum, but your K will be at a max. And same thing with V, it'll be V max. And then it will overshoot it and become, go to the left side by that same distance that it was initially like pulled. And, as you would expect, that would be again a max, but a K or kinetic energy of 0 and velocity of 0. Now, does this make some sense?
Yeah, yeah, it does.
Okay. Now, when we talk about, let's see how I can put this. So, yeah, so okay, for the spring mass system, I'll use blue. We can, so what helps me remember this formula here is going to be like Kickum, with a K, and well, I should have said a lowercase k and like a lowercase m. So what this means is that the frequency, and there's a 2 pi term here just to deal with radians, but it'll be times the square root of k, which is the what's k? What do you think? Little k.
Like a spring constant?
Yep. Good. So uh yeah, so it'll be times the square root of little k over mass. And so we can see essentially that the frequency is going to be proportional to k, or the square root of k. So that spring constant is the restoring quantity. Like that is what is responsible for when you pull something that's attached to a spring, that it will return back to its original, well, it'll try to return back to its original position. So that's the restoring quantity. But the mass is or causes it to overshoot. Because if something has a mass and a velocity, it'll have a momentum, and that will cause it to overshoot. So it'll go too far, then it'll kind of come back and try to go back to that equilibrium state, but it'll overshoot, like going back to the right as well. So that's a way for us to, I guess, conceptualize the um, something in like simple harmonic motion in the case of like a spring system. Um, what do you think about that?
Yeah, makes sense.
Okay. Um, yeah, and then also like, okay, I guess I should also I'll put a little aside for the like the 2 pi like radians thing, like essentially 360 degrees, which is one full cycle, is 2 pi radians. So a lot of times either, you'll use the 1/2 pi thing to convert radians into, either degrees or like one full cycle. So a lot of times you most likely won't even need that 1/2 pi part. But this, yeah, so this is the simple harmonic motion for a mass on a spring, and you're saying that that makes sense, right?
Yes, it does.
Okay. Now, the other type that we would see would be like a pendulum. So
Mhm.
like let's say we have, let's see, like some mass or something that's hanging down, um and oh yeah, I'll do the same thing with like the equilibriums and stuff. One second. Okay, so here it's at this equilibrium like position. So if you like pull it kind of like back to, let's say, um here, um that's when you like kind of initialize it. So like, yeah, let's say that this is going to be, or maybe I could do it like this. So this could be the time equals 0 seconds part, and um and then yeah, then this would be if you know, kind of like pulled it up like this. So let's say that's time equals 1 second, and you're essentially like doing the thing where you with a spring mass on a spring where you like pull it away from equilibrium, and then its restoring force brings it back or tries to bring it back to equilibrium. So from this position here, right, we have like this position here. I don't know if you could see my cursor. Yeah.
Yeah, I can see it.
Yeah, so it'll be like this over here. Because here it'll have by the way, what type of potential energy would a pendulum experience?
Mm,
So a way to think about it would be, what would be the restoring like quantity here? Like what would cause this pendulum to go from here back to here?
gravity?
Exactly. Very good. Very, very good. So yeah, gravity. And yeah, that's the thing with potential energy. Like a lot of people like use like PE or something for that, but like physics in it's the proper way to put, like I would write would be the U with a subscript indicating what type of potential energy, because there's a lot of types, right? But yeah, the potential energy will be at a max here, right?
Yes.
Um and the kinetic energy is going to be at 0 here.
Yeah.
All right. Yeah, I guess like I don't even have to write velocity since kinetic energy, implies that. So yeah, when you let this go, it will, well, go back to, this uh state here, and beyond that, it'll go here, right? And then it'll come back. So that's at t equals 3 seconds, let's say. So at this t equals 2 seconds, what would its potential energy be? What would its kinetic energy be?
Um, I feel like potential energy should be 0.
Uh-huh.
Um, kinetic energy. Hmm, I don't know, because it does overshoot and go on T3 more.
Uh-huh.
Um, but
So,
it's not max. I don't know.
well, so we can think about it just like we thought about simple harmonic motion on the mass on a spring to the left.
Yep,
So, yep.
I see. So
Mhm.
when it's right at like sort of the equilibrium position, it's a maximum kinetic energy.
Yep, exactly. So, yeah, when it comes back to that equilibrium position, it's at its maximum kinetic energy. And I put like a minimum potential just because I don't think it's going to be like 0, but yeah, good. Okay, so like K would be K max, and then it'll go further to the left, which will be again just like it was on the right. So potential energy of max and K of 0.
Yep.
Okay, so for this, the mnemonic that I remember is just glide like this with the little g and the capital L. And so what that means is that your frequency will be 1 over 2 pi square root of little g over the length. And the length, by the way, is just the length of the string that the pendulum is attached to.
Okay.
But yeah, the G is the restoring force, so the restoring, quantity, and the length is what causes it to overshoot. Because the length, if you can imagine, kind of like a torque system, the longer the length is, the further it will cause it to like overshoot.
Yeah.
So yeah, so okay. Now um okay, now for these, so yeah, for these are like the two main ones. Now, if we go back to, I guess, sine and cosine terms, like you can use sine and cosine terms to express simple harmonic motion because, like, let's say that you had a, for like this spring system, right? Let's say that you had like a vertical disc with a little, let's say like a circle or like a dot on it to indicate where that mass is. So like we would start here, right? And then we would pull it so that, it lines up over there. And it'll go back here to its equilibrium position. So like this would be at t equals 0. This would be at t equals 1. This will be at t equals 2. And when it overshoots over here, oops, over here, it'll be at t is equal to 3.
Yeah.
So the reason that I'm showing it like this is because if you take that disk, let's see if I can add something here. Uh, uh, so I put this disk thing, and if you double click on it, it should like animate.
Yeah. Yep, it's animating.
Yeah, you can see how that's what I mean about the disk thing. So it can take if you just consider this movement of this point on a disk, if you just consider it in one dimension, it'll be, yeah, in one dimension, it'll be just this line on the bottom that goes left to right. And then we have, if you wanted to, so that means if you wanted to then express it as, oops, yeah, so try that. Does the other thing work?
Yes.
Yeah, so now you can see how we can have this mass on a spring. And it's just like the one that I drew, except I drew the one, being horizontal. This one is just vertical. But you can see then how like the disk part helps take that one-dimensional simple harmonic motion and shows it in 2 dimensions, so with an x and y dimension, and then that means that you can then plot it with an x and y axis, and it'll give you a sine curve.
Okay.
So that's why so that's why simple harmonic motion, can involve a lot of, sine cosine terms.
I see. Yep.
Yep. So okay. So that's simple harmonic motion. Um, see if I can, let's see. So let's try this question here.
Which of the following statements is true regarding simple harmonic motion? A, the acceleration of the mass in a mass spring is always opposite the direction of displacement. I think it has to be in the same direction. Pulling a mass spring to a greater initial displacement increases the frequency of oscillation. I think it's not part of the, wait, mass spring. Mass spring and not the pendulum system. The mass spring, it's only dependent on the constant and the mass, so I don't think it would. But let's see. The displacement, velocity, and acceleration of a pendulum bob do not all vary sinusoidally. So displacement is following a sine wave. Velocity, acceleration. I feel like velocity and acceleration should, okay, be in the same direction, but are they varying sinusoidally? They are going from like 0 to like max to min, so I will say maybe yes. Let me see D.
You said 0 to max.
Sorry,
So you just said 0, it goes from 0 to max,
I guess
and then it goes to what?
minimum. I guess I'm thinking of the oscillation, but if it's sinusoidal, it has to start at max,
So
not min, or not 0.
so let's just think about that thing. So you said 0 to max to min, right?
0 to max is 0 to min, I guess.
Oh, well, no, so you had the right idea here, right? Like if you go from 0 to max, right, you're gonna have an acceleration in that direction, right? But to go from max to min, you're going to be decelerating, right? Like think about, if you're in a car and, well, let's say you start at 0 velocity, right? And then you start moving with some velocity, so velocity greater than 0, but you have to go back in the opposite direction. That means that your velocity is going to have to go, you know, is going to have to decrease until it hits 0, and then it'll be negative going in the left direction.
I see.
So if we think about this stuff here again, so I guess I should have written something like, instead of velocity, acceleration, because that would tell us a little bit more. So let's try that. So for the spring mass system, when t is equal to 1, and from t is equal to, so okay, we go from the 0 equilibrium state to the, delta x to the right state. And from there, it goes to the left, right? So if it goes from this position to this position, it's going to be moving to the left. So that means that it's going to, well, again, if it's at this position, its velocity is 0. At this position, its velocity is at a maximum. So we're getting a change in velocity, right? And that's the definition of acceleration, right? So we should be seeing that. So here I would say, so yeah, I'm going to get rid of the velocity terms because we already know that from the kinetic energy. But what can help us is acceleration. So here, the acceleration will be, let's say, at a max in that direction. And uh, by the time it hits, it'll overshoot the equilibrium point and then it'll go to the left. And here it will have a max acceleration also just in the opposite direction.
Mhm.
So we go back to this question here. Um, so which is true? So okay, so you were able to eliminate B, right?
Yeah.
Because the frequency of oscillation for a mass spring is would be dependent on mass and uh the elastic spring like potential. I mean a constant. So, but this pulling it a greater initial displacement, that's delta x, right? So that would have something to do with like the force, like elastic force, right? But okay, so B is out. Then C talks about the displacement, velocity, and acceleration of a pendulum do not all vary sinusoidally. What are your thoughts there?
I guess I'm thinking of like sinusoidal is what that is meaning. It just means that it's going as a sine wave. And we did draw this here that like the position is going sinusoidally.
Uh-huh.
Um, so that's for sure. But
So,
the velocity is going from not moving to maximum acceleration, and then from maximum acceleration to I think it is varying sinusoidally.
yeah, yeah,
And then yeah, I think it is, and it's going on the opposite direction. So I think it is varying sinusoidally.
yeah. So sinusoidal won't just mean sine curve, it'll mean like all of that stuff. Because like sine and cosine are essentially the same thing. They're just out of phase by like 90 degrees. So yeah, they do vary sinusoidally, which what would also mean like in a cyclic fashion. So okay, so that's out. And then what about D?
Displacement, velocity, and acceleration are all in phase with one another. So I'm thinking what they mean by in phase.
In phase. So that would mean so like how I said that sine and cosine are out of phase by 90 degrees.
Mm.
It means that if you took one of them and you moved it 90 degrees in one direction, it'll be equal to the other thing.
Um, but they're
Mhm.
um are they all in phase with one another? Let me see.
Mhm.
Um, yeah, I would say so.
So let's see, right? Because we have potential energy and well, acceleration is a max when velocity is a min or zero, right?
Yes.
So for D here, it says that the displacement, velocity, and acceleration are all in phase.
I see.
They should be out of phase, right?
Yeah. I guess I didn't understand what you meant by phase then.
Yeah. So
Yeah.
so yeah, so phase would be like, okay, so like if I whoops. So, you know, let's say that's a sine curve. That's a cosine curve. And, this is, whoops, like 90, 180, uh, to 70. I mean, that isn't perfect. 360. Um, so you see that so if I take I'll make it purple. So let's say that I take the sine curve, right? And I move it to the left by 90 degrees. So that means that so this point here at 90, which is at 1, right, will have to be here, right? If I move it to the left by 90 degrees.
Hmm.
And this point here at 180 degrees, where it's equal to 0, will be where the 90-degree part is, right?
Yeah.
And then here it's -1 at the 270 degrees, the sine curve. And if I shifted it to the left, right, it'll be at the 180.
Yeah.
So you can see that if I did that, if I took the sine curve and I shifted it 90 degrees, to the left, it will be in phase with the cosine curve.
Okay.
So that's what in phase means. And then out of phase is what you have here, where they're out of phase by 90 degrees. So you want to consider the fact that, or like maybe you could help by thinking like, like I guess, like like a swing. Like, have you ever been on a swing? I don't know.
Yeah, I think the wave example helped.
Yeah.
I got it with it. Yeah.
But yeah, if you're sitting on a swing that's going back and forth, right? Like
Mhm.
as you go up to like your highest point, you stop, right? And you're about to be going backwards. So your acceleration is pulling you backwards. And then you go down and the fastest point at the when you're on a swing is at its equilibrium point. And then it'll overshoot and it'll be, oh yeah, I can show you the drawing for the answer. So here we can see that you have, so this spring over here, this mass on the spring is being pulled to the right by a certain um, displacement value. And that's where it'll have no velocity, but a maximum acceleration because it wants, like, when this is let go, the velocity is 0, right? When it's let go, the velocity will start to increase going left. And whenever we have a change in velocity, we must have an acceleration. And so here, at its equilibrium position, it's at its max velocity, but it overshoots to get to this point here. And at that point here, um, it'll start to slow down and stop. So it will be like a velocity of 0, but it'll give you an acceleration back towards equilibrium. So your acceleration is back to max, then back to this middle point where the velocity is at its max, and then back to this point on the right where the velocity is 0, but the acceleration is max.
I see.
Mm-hmm. Yeah. So that's something about um the yeah, the simple harmonic motion stuff. So okay, now let's think about, I guess, to get to the topic that you were talking about, let's talk about the types of harmonics. So basically, okay, so we can have, okay, so there's something called dampened harmonic oscillation. And what this means is that so like for oh, and the reason that I'm talking about simple harmonic motion is because that's the larger like umbrella that includes the stuff like harmonic resonance, which is basically all in standing waves. So
Okay.
all of the stuff that we're talking about today is standing waves where they don't move, they're in place. So uh so yeah, for a standing wave, you can imagine like attaching a rope to like a wall and then being like at, away from the wall with the rope and you just kind of swing it like that.
Mhm.
So okay, dampened will mean that amplitude and energy decrease over time, but frequency and period, which is 1 over frequency, stay constant. And that's just like any type of standing wave that over time it'll just weaken. But the opposite of that is resonance. So that's the opposite. So that means that one object vibrates at a certain frequency, which causes another object to vibrate at the same frequency. Okay. So what we can then so what we can then um see would be so okay, so let's say that we have so I call them even, which would mean either open, open, or closed, closed, type of um I guess like resonant or harmonic system. So that like if I were to draw it, that would look like okay, so that would be like um or yeah, oops. Okay, so I have a closed one that I drew and an open one that I drew.
Mhm.
And what happens here is for the um for the closed. So okay, I'll just point this for the open and this for the closed. So the open is going to have so the so like the point, let's say this point here is 0, this point here is 1, this point here is -1. So when it's at 0, we call that a node. And when it's at its maximum point, like 1 or -1, we call that an antinode. So for the closed system, there are nodes at each end. And for the open system, there's antinodes at each end. And if we start to think about this in terms of, so let me copy that, or rather, copy the entire thing. Oops. Okay, this is gonna be kind of I can't move. I'll just draw it separately. So say we have that, 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 that. So okay, now if we just take like so what I drew over here, like I drew like the two different types of waves that it can be, but in actuality, it'll just be like, oh damn it. It'll be just like one of them, like this, right? So let's imagine that. So we can draw here, let's say this will be something like, are we gonna say something?
No.
Yeah. So okay, let's say that that's like that. And like this over here. And so if we were to think about like the wavelength here, right? Let's say that the length of one of these rectangles is L, right? The wavelength of this wave would be how many L?
Mm. Like the entire thing,
Just for like a wavelength.
I guess 4.
So to figure out a wavelength, right? You want to look at the wave and see at what point does it restart.
Oh, I see. Um, so 2 L's. Hmm.
So one wavelength here is equal to 2L. Okay. Now the mnemonic that I guess I think about for this is um when I see someone with a guitar I frequently envy their tool with a 2L.
I see.
And the
Okay.
NV of envy underlined. So what does that mean? It means that if we wanted to figure out the frequency and that subscript n is to indicate which frequency you're trying to obtain. So that'll be equal to NV over 2L. All
I
right.
see.
And so if we had, for instance, yeah, so let me see. So we have, okay, so when n is equal to 1, we have what's called the fundamental frequency. And this is also called the first harmonic. Okay. And when n is equal to 2, this is called the second harmonic, which is also called the first overtone. Okay.
Okay.
And then if it was n3, this would be third harmonic, second overtone, right? Yeah. Now, um, so if we were to, so okay, so in the equation that I wrote with the Fn here,
Mhm.
we can kind of think of that. So like, okay, so like for this, it would be like F with the n is equal to 1, and then n is equal to 1 here, V over 2L, right? Now, F with the n value being 2 will be 2V over 2L, right?
Yep.
But what we can do is, since F1 is equal to 1V over 2L, like this is just the same thing as 2 times 1V over 2L, right?
Yeah.
Which is the same thing as, 2 times F1, right? So that's like a bit of like a shortcut there.
Mhm.
But yeah, so that's what happens with um the like an even system, harmonic system. But we also have the odd, is what I call them, which can consist of, closed, open, or open, closed. And what these will look like they'll have just one node or anti node at each end. So for instance, if I drew this closed open system, it will look like, either that or that, right?
Yep.
And if we had open closed, it would be like something like that, right? Like that. So for this, let's now think about what or how many of these would produce a like single wave. So if we have a node at one end and an antinode at the other end, like it would be like, oh, and I guess the way that I drew it, like it looks like that. I mean, I wish I can get rid of like
The line in the middle. Yeah.
yeah. I tried before just drawing like a line, like tracing it. Okay, I could do that. It didn't work before, but damn it. Okay, whatever. So that, and then that. Oh, that's so annoying. Okay. Oh, there you go. Um, well, okay, whatever. That's fine.
Yeah. Yeah.
Okay, so we're gonna have the um let's say like I'm just gonna make some demarcations here. So like yeah, so let's say that we have, something going like up there and then coming back to the 0 here and then going down to the -1 here. Um and then coming up at wait, 1, 2, 3, yeah, 4 would be like something like that. Kind of hard to see. This is the 0, this is the 1, this is the -1. Um,
Yeah.
so
And which end is closed here?
oh yeah, it could be, I guess, like any of the ends. Like this drawing is a little weird because like yeah, it could be so okay. I guess usually you would have the node at the like closed end, so maybe the left side would be the closed end. But the reason that I'm showing you this is because uh if this is equal to L, right? What would be the wavelength for this?
The entire thing.
Uh-huh.
Yep.
And how many L's do we have here?
4. 4.
Yep. So the wavelength for an odd system, like system, would be 4L. Okay. Now, so what that means is that we can express that as so Fn is equal to Nv over this time 4L.
I see.
And the N, by the way, has restricted values. It can only be odd. So like 1, 3, 5, etc.
Okay.
And the fundamental will still be um an N of 1, right?
Yes.
And that is still going to be the first harmonic, but the next one will have to be N is equal to 3, right?
Yeah.
And that means that we skip the second harmonic to get our third harmonic, but we still call it the first overtone.
Okay. I see.
And then we would have N is equal to 5, which would be the fifth harmonic, which would be the second overtone.
I see.
right? So that's for the, yeah, so that's for that. Now I can show you, let me get like a picture here. Uh, okay, so I have examples here. So like on the left side, we have, so like yeah, on the left side here we have like an odd system. On the right, we have an even system. So we can see that the fundamental frequency, or the first harmonic for the odd, has one node. The node will be at the closed end, and the anti-node will be at the open end. And that's it's 1/4 of a wave, because we know that the we need four of these lengths to get a full wavelength.
I see.
And then for the first harmonic for the even, we get half of a wave, so we can get one node and two antinodes. Um, and then we have the third harmonic for the odd, which is the second harmonic for the even, but they're still the first overtone. And you can see how this pattern continues.
I see. So let's see. Um, First harmonic, third harmonic, you have two nodes. So it's more like the, what is it? The overtone.
Hmm.
I mean, I guess it's still first overtone, but it's
Yeah, so like the way
differentiated
that I would
from.
view it is that we have the fundamental, which will always be the first harmonic, but then after that, the harmonic becomes uh either something or something else. So I would think about it as, so first harmonic is fundamental, and after the first harmonic in fundamental, you have the first overtone, and that first overtone will be the third harmonic for the odd, second for the even, and then the second overtone would be fifth for the odd, third for the even. So yeah, I would think about it like that.
I see.
Yeah. Then I also wanted to post, yeah, this.
It's
Um
kind of like the number of nodes is actually more like the overtone number plus one.
yeah, I was gonna say like an N and N plus one type of thing.
Yeah.
So yeah, you have the right thinking here. Like essentially, right, if you just take the N of the, well, I shouldn't say N. If you take the number of the overtone, right, and you add one to it, you'll get that harmonic for the even. Um, but for the odd, you would have to take that and add two.
I was thinking more of the number of nodes. So like if you take like second overtone will always be like two plus one nodes.
I
I
see.
mean, either odd or even. Same for third would be three plus one, so four
Yep.
node. Yeah.
Yeah, yeah, totally. So yeah, good. And then yeah, here I wrote drew or pasted this picture of open at both ends, first harmonic.
It says fail to load.
Oh, me. Here, let me try this.
Now I can see it. Yeah.
All right, yeah. So here we can see that open at both ends, same thing as closed at both ends. First harmonic, wavelength is, 2L, frequency is F1, and then, the wavelength for the second harmonic will be the L, the L value there. And you can see how essentially what you're, I guess, changing is just uh the the number in front of the frequency value for the whichever harmonic it is. Um, and then the length, the wavelength rather. So that's for that. And oh yeah, I have another image that can help. I think this is from UWorld here. Does this load?
Yes, it did. I guess I'm still trying to understand the wavelength here on the other graph.
Oh yeah.
The one you put right before, the one with the red.
Yep, yep.
Yeah. So what is it? So for, I guess, open or close at both ends, first 2L. And for the second harmonic, it's just L. And how are you getting that again? Like how are you getting the wavelength value for like the second or third or like the other harmonics?
hmm Yeah, so if we look back here, right, we can see that for open at both ends, which is even, um,
Uh-huh.
that the first harmonic is half of a wave.
Yes.
So yeah, so if we think about, so for instance, here we could say that, so for the even, the wavelength is equal to 2L, which would mean that um that wavelength divided by 2 is equal to the L. So here we could see that this is just an L, like the length of 1, and within L, there is half of a wave, or which would have a value of a wavelength of half of the wavelength. So here we can see that with the second harmonic here, that the wavelength is going to be the entire L, because what you're doing when you're creating that second harmonic is you're adding more nodes and antinodes, and meaning that you can have more waves within that same length.
Okay. Is
So,
there a formula for that for like wavelength, or do I just have to like memorize
oh
like
yeah,
L to
yeah, so we can just remember that, um, that the well, so like velocity of a wave is equal to the wavelength times the frequency. So if we solve for a wavelength, it would be the velocity over the
frequency,
frequency.
which we have the formula. Okay, now it makes sense, I think.
Yeah. So this would be like um 4L. It'll be the inverse of the F. So 4L over like the NV here. And then for the wavelength here, it would be the 2L over the NV.
Yes.
So yeah, so that would be the wavelength, right? So like for instance, let's say that um if n is equal to 2, right, for the um second harmonic, uh that the wavelength at 2 is going to be 2L over 2V, right? And the 2's
Mm.
cancel. to give you L over V. And the V isn't really important because uh yeah, the V isn't really important here, but we can essentially see how the if you're doing the second harmonic, or sorry, yeah, the second harmonic, the N equals 2, and that cancels out the 2L, so we would get our wavelength equal to L.
I see.
Mm-hmm.
Let me see with 3. So this is, we're doing odd. So with 3, just 2 times 2L over
When you say 3, which one are you doing?
the third harmonic for the odd.
Oh,
Just
so what I
2.
showed you over here is an even,
It's an even.
the one that I showed here.
Okay.
Yeah. So,
So I guess we could do 2. Um, wait, we did 2. It's 3. I just want to make sure it's,
hmm,
I get it 2L over 2 thirds. But it's the inverse. Hmm. Okay, yeah, I get it now. Yeah,
uh-huh.
took a moment. Yeah.
Yeah, yeah. And like for the odd system here, right? It's just with the 4L. So if you wanted to do let's say you wanted to find the fifth harmonic, the wavelength of the fifth harmonic, right? That would be 4L over 5V, which would just be, I mean, I'm not going to consider the V really, but it'll be like point,
4. Yeah.
yeah, times the length, right? And then if we look here, we could see over here, it's 4L divided by 5.
Yes.
It's zero point 0.8 times L, right?
Yeah. And why is it that we don't consider the velocity?
Oh, I mean, because the velocity is going to be constant. Uh, because these are so like, all right, so the strength, these are all standing waves, so the waves themselves don't really move, but the if it's like air, like in an instrument or something like that, it would be like velocity of the speed of sound or something like that. But we don't like we do consider it, but it would be the thing that would cancel out if we equated the two, just because velocity is equal to the wavelength times frequency.
Okay. Yeah.
Yeah. So okay. That oh, and then you can also see here, um, the same thing. Like you can kind of see how they just said who cares about the velocity here.
And where are you? Where are you pointing?
Oh, this, do you see the image here?
Yes. Yes. I can see.
Yeah. Uh so yeah, it says that the wavelength of the nth harmonic, the length, frequency of the nth harmonic, and the speed of sound. And so we can see that these values here, the L is 1.25 meters, the V is the speed of sound, 350 meters per second. And so when they do the FN calculation, they're going to be like including that velocity term. But once you have the velocity term, you could just invert that, or sorry, once you have the frequency term, you can just um invert that or take its reciprocal to get your wavelength value.
Okay. Yeah, that makes sense.
Yeah. So that would be so that would be the thing for in terms of like antinode and node. So um so yeah, this what do you think about this?
It makes more sense.
Uh-huh. Let me see if I can find.
It's not too hard to forget, I feel, now that I get it more.
Yeah, yeah. So okay, did you have like a question, like a UWorld question that was like what was it? What
Yeah.
sent?
Yeah. I can share my screen. Good.
Yeah, you can let's have you email me that screenshot again because I can just paste
Okay.
it onto this and then you can
Okay.
just, export this as a PDF.
Yeah. I just sent it.
Okay. Let's see. Great. Okay.
Okay. So they're asking me, according to this table, which of the following, I guess, I have to look at the table, makes noise at a frequency that resonates in the bore of an MRI magnet. And they're giving me the speed of sound.
All right, let's see. So MRI is a common non-invasive medical imaging method with high resolution and soft tissue contrast. The main component of the MRI scanner is a very strong superconducting magnet with a magnetic field strength measured in Tesla's T. Um, by the way, that's this, right? Magnetic field strength, right?
Yes. Well, what's that formula for magnetic field strength? Is it the same as like magnetic field, or is it like a different one for the strength of it?
The magnetic field strength, you'll see different kinds of things that they could express that as, which would depend on basically the uh like there's a lot of different ones. Like for instance, there's like magnetic field of a straight current carrying wire. There's magnetic fields of like these different type of systems. So the magnetic field part, you know, we can talk more about that
Yeah.
yeah next time, but it's not going to be very, it's not like a simple thing to kind of measure.
Okay, I see.
Yeah. um but okay, cool. So if we look back here, so yes, okay, field strength measured in Teslas. Okay. The magnet resembles a large pipe, 1.25 meters long. That's the L, right?
Yeah.
Open on both ends. Okay, that's nice. So that's, even, right? With a bore diameter of 0.6 meters. I wonder if that would come in, but I would just put in.
I don't, I mean, when I was reading this, I don't even know what a bore is.
Oh, okay. So like, let's see. So to bore something means to kind of drill a hole in, kind of. You know, like, uh, so you know how like climate um scientists, they use like what's it called? They like use so they have something that kind of like goes into like ice in like
To get
Antarctica.
a sample?
Yeah.
Yeah. Mhm.
So they get like a vertical amount of like the ice and they can pinpoint, the time periods and look at stuff in, the different types of things in the atmosphere and stuff like that. But when you bore something, you're essentially drilling a hole in it.
Okay.
So yeah. So I'm just thinking of the thing where they drill it's because it's like a circular kind of cylinder that they drill into, like, the ice or whatever, to get that cylinder of ice. And yeah, and the bore diameter is just the diameter of that hole that's being made or drilled in.
I see. Yeah, I get it.
Yeah. Like Elon Musk has a company called the Boring Company, which the idea behind it is to make these tunnels underneath where your car can go in, and it can, like, it's kind of like a subway system kind of underground. But anyway, yeah, that's what the bore part means.
I
Um,
see.
yeah. So okay, so we have that. Then they say that the magnetic field is generated by an electric current flowing. Okay. So that's this thing with coils, because you could see here in this one, there's coils, right? So
Yes.
yeah, so let's see. Okay, so all right, and then electric current, right, is the movement of electrons, and the moving charged particles produce magnetic fields, so that makes sense. Uh, Coils of superconducting wire. The superconductor is cooled to 4 Kelvin with liquid helium and has zero electrical resistance. That's essentially what a superconductor does by making it super cold. Liquid helium that boils out of the MRI scanner is stored in a collection system, cooled back to a liquid and returned to the MRI scanner. Okay, during imaging, the MRI scanner generates rapid magnetic field oscillations that cause vibrations and loud sounds. Researchers measured the sounds of MRI at different magnetic field strengths and compared them to common noise sources. Okay. Table 1 lists the sound intensity in decibels and predominant frequency for these sounds. And then we have table 1, sound intensity and predominant frequency intensity from different noise sources. Okay. So, um, tell me your approach here.
Let me see now with my new knowledge. According to the data in table one, which of the following makes noise at a frequency that resonates in the bore of an MRI magnet? I guess here, like when they say resonance, I was thinking like, are they referring to like the fundamental frequency for that? That was my first thought.
So, all right, I guess I should have said let's look at table 1 first. So, table 1 says sound intensity and predominant frequency from different noise sources. Um, so we have noise source on the left and sound intensity in decibels, and then the predominant frequency. Um, Tell me about decibels. Do you understand that?
Yeah, they're logarithmic, and so like every like increase, like 10 unit increase is actually like 100 increase. Yeah.
Uh-huh. So, okay. So we have the noise source. So the MRI with these different Tesla values or magnetic field strength values. Um, and it seems like, so we want to figure out proportionality relationships, right? So what proportionalities do you see?
It's directly proportional, like with noise. So the magnetic field strength
Mhm.
with sound intensity and frequency, all
Yep.
directly proportional.
Good. So I could say magnetic field strength is proportional to, like, the loudness in decibels. It's also proportional to the frequency in hertz. Okay. And then for the gas lawnmower, we have a lower sound intensity and a lower predominant frequency for the vacuum cleaner. Even well, uh, even lower sound intensity, but way higher frequency, right?
Yes.
Okay, cool. So, all right, according to the data in table one, which of the following, okay, makes noise at a frequency that resonates in the bore of an MRI magnet? Note the speed of sound in the air is 350 meters per second. Okay, so yeah, so what do we do here?
Mm. Um, I mean, zero frequency. I guess we're giving the velocity. Uh, we know the length. Um, I don't, I mean, I guess they want us to look at the table because the table is giving us frequency values, which we can find with the formula. Like, I guess I know that relationship, but I don't know why we're doing it. Like, I could plug in things, but like, why am I doing it?
All right, so let's see,
Um,
right?
like, I still don't understand the part of that resonates in the bore of an MRI magnet.
Uh-huh.
Yeah.
So just forget about it being a bore, but think about it in terms that we know and understand, like as a pipe, a large pipe. So we know that it's even, which means that its frequency would be this, right? And we know that its length is 1.25 meters, so we have a length value. The velocity is going to be the speed of sound in air, 350 meters per second. So we have the V velocity value, right? And
Yes.
now we want to see um uh let's see. We want to see um something that makes noise that would be so we want to see okay, we want to see something in table one that should give us a frequency similar to the frequency that's given to us in the question stem. And they're so they're telling us, so let's find out what the frequency is for this magnet over here.
For which frequency? Like the first frequency?
That's a good question. So, um, well, let's see. Um, yeah, I would say that since they're not telling us anything about, you know, different n values, right?
Oh, I guess we could just find the first one, right? Because as you mentioned earlier, they're all multiples of each other, right?
Yep. Yeah.
Yep.
So yeah, so I guess no matter what, you would start with the fundamental frequency. But I would also say that since this is not mentioning anything about different harmonics, then what we should do is find the fundamental. But
Okay.
also for what you said. So okay, let's try that, right? So we can plug in to this.
Like 140 is what I got.
Okay.
140 makes no sense.
Um, okay. You said you got 140. So which of the following? Okay, we can work with that. So let's now try to figure out if there's going to be some what is it? Some other harmonic that would give us the 700, or well, I guess I shouldn't say 700 because that's us like already knowing it, but let's see what we can do with the so okay, you said 140 hertz, right?
Yeah.
So um that's a fundamental. Whoops. And the second one would be 280, right? And
Yes.
then the third one would be um I guess 3 420. Fourth one would be 560. Fifth one would be 700. Um
Yeah.
yeah, let me think of a better way of solving this.
Yeah, I feel like that would take a long time.
Yeah. So let's see. Okay, so let's do this. 700 here, 1000 here, 1500, oops, 1500 there. Gas lawnmower, 250 here. So, oh, was there anything below?
Yes, there was the passage continued.
Did it maybe that gave us some more information?
I can check. Let me.
Yeah, because yeah. So yeah, you could check that and I'll try doing something for these.
Okay, I sent you the rest.
Okay, the noise frequencies were determined using frequency selective RC circuits with a resistor R and a capacitor C in series. Sounds with frequencies above the cutoff frequency FC of the circuit were suppressed. The value of FC in hertz was calculated with equation 1, which is 1 over 2 pi RC. Oh, the resistor. Okay, capacitor. Okay. MRI can be combined with another imaging method, positron emission tomography. PET to detect cancer. PET imaging maps the uptake of radioactive metabolite. Radioactive decay emits a positron that annihilates with an electron and forms gamma rays that are imaged by the scanner. Oh, okay. This doesn't really, I don't know if this really helps here, but
I guess one thing we can look at the answer to see how they solved it in UWorld.
sure.
Um, it's kind of long to screenshot, but I guess I could do it. Should I also email you that?
Yeah, I think the top part I have already, the resonance and MRI bore on open on the two ends over here.
Okay.
Oh, you know what? I think this is a solution here.
Okay, it seems that they were doing what I was thinking of the solving for the fundamental, and then it would be something n of that.
Uh-huh.
Um, so actually, the simplest way it seems that they did it is by taking the frequencies from the chart and just dividing it by the fundamental and
Oh
seeing if you
yeah,
get a whole number.
that's what I'm doing over here.
Okay.
Yeah,
Yeah.
over here. See, so I just wrote,
Oh, I wasn't seeing. I was just sending you all this.
got it. Yeah, yeah. So yeah, so I'm just doing that. So like because yeah, so 140, okay, so um oops. So oh yeah, so you sent me the other thing?
Yeah. I guess it has to be like a whole number. Is this a whole number? Like when you did the divisions? Or
Yeah, but I also get the 7 and stuff. So yeah, let me see here. 140 N hertz. Okay, and then 700, all right, divides into 5, and then the other ones, not multiples. Oh, I guess I was rounding. So because this should be like 0.14, this should be, well, that one should be 1,000 over. Okay, okay. Yeah, this would be, well, 7 goes into that twice, goes into this, wait, goes into this twice, goes into this 20 times. Then that's the 10. Yeah. So okay. Um, okay. So by the way, this passage talks about a lot of really good stuff that we went over, like
yeah,
in what you showed me after, like positron decay and stuff like that.
yeah,
So yeah, it's a good passage to be doing. But yeah, but I think the best way to approach this, and you can obviously see it's a really tough question because there's such a split between all the answer choices. Like usually I use that to gauge how good of some like a question is. Some people think it's the opposite. Some people think like, this would mean that it's not a good question, but that's not true. Was if like 96% chose the right answer or whatever, that wouldn't be that good of a question. But this is a good question because there's like complete like nice spread between all the different choices. Now, I think that the choice that you made would be the most tempting because when we did our math and we got 140 hertz, the gas lawnmower is closest to that, right?
yeah.
Like the 250 is the one that's closest to the 140.
Mhm.
But but we want to answer. So like the question's telling us, like it's not saying which of the following makes noise that is closest to the frequency that resonates in the bore of an MRI magnet, right? They're not saying closest, right? They're actually saying like exactly, right? So, but I totally understand why you would want to pick the 250, um, because it's the closest number to 140. But yeah, but aside from that, I would essentially do what we did, which is take our 140 value and divide it by, like, so each of these choices, I would write down the predominant frequency. So I wrote 700, 1,000, 1,500, 250. And I divided each by 140. And what I'm trying to find is a uh integer, um like a whole number.
Yeah.
So yeah, definitely tough question. Um, but at least we're dealing with, even, but yeah, so you would essentially just take that information that you correctly highlighted here and see that it's open at both ends, so you know which formula to use for the frequency. You have the L value. Sure, there's the radius term here, but this question doesn't require us to do anything with that. So yeah, so I would start off by, when reading it, writing out these proportionalities, and then when answering the question, figuring out what's the fundamental frequency of this MRI bore thing, and we get 140, and then from there, like I did it this way first, but you know that this would be super time consuming. So doing it this way, where you essentially just go through the choices and figure out which ones would give you that nice whole number for the frequency,
That's good.
that would be uh what you would do. So yeah, do it that way.
Sounds good. This is useful.
Mhm.
Um, I would you be able to send me the previous whiteboard because I downloaded it and I don't know where it went. Like I don't know where it saved it to in my computer. I couldn't locate it.
Uh-huh.
Like the one from yesterday.
Uh-huh. So yeah, so let's see. So why don't you save this one first? You could do the export PDF.
Yeah, I have it.
Okay, and now I'll go to the whiteboard from before.
Okay, I got them.
Okay, awesome. So uh what are you doing tomorrow?
I am undecided. I don't know if I should keep practicing and like drilling questions or if I should and take my or if I should take my practices tomorrow. Like
Hmm.
either way I would take it either Saturday or Sunday.
Hmm.
But yeah, I need to decide soon.
Okay, okay. So and the test that you're going to take, let me just take a quick look at this again. Um because your test is still April 13th, was it?
Yes.
So um okay, you'll take one like third party full length 4 this weekend, and then 5 the next weekend, and then 6 the weekend after that. And I guess we talked about not doing the AMC tests because you did them really recently, right?
I did them last year.
Okay. So let's see. You said that was August 2023.
Yes.
So which AMC test uh is one where it's been the most time since you've taken it?
Yeah, I wrote that down. I wrote like, so either number 4, the free one, or the sample.
Huh?
It's been the longest, like probably like uh April of last year.
Okay, okay. Yeah, you said it was the full length which full length and which.
AMC number 4, the 2022 one, I think, which is also called the free practice test and the sample test.
Okay, let's see. Okay. I think that let's see. Sorry, so you said the test number 4 and the sample?
The free practice test, the one that's like 2022.
That's the unscored that's a scored free test, right?
It's a scored free test, yeah.
Yeah, okay. So and which one did you take like uh like
Um, I think it was number 4. Like the of those 3, those are the most far. I think the least frequent one would be number 4.
Mm-hmm. Okay. Let's have you do the third party for this weekend and then for third party for next weekend also, and then April, like the weekend before your test, you will take the AMC full length, um, the like the newest one. I think I call that full length 5.
Yeah, sure.
Uh, how did you do on that before? I mean, if you don't remember exactly, that's fine.
I can locate it really quickly.
Huh? Because yeah, I'm looking at the notes from when we first met, and I think you were telling me something like the AMC full lengths you were getting like 517s.
The highest one, yeah.
Okay, but the rest were like.
Let me locate it.
Mhm.
Yeah, so on full length 4, I got a 506.
Uh,
And on the scored one, 5, full length 5, a 510.
okay. And then sample.
Sample, let me see. Unscored, that was 191 of 230. I don't know how. Yeah.
Okay. The breakdowns for the 506 and the 510.
Yeah. We'll have to go to product. Okay, so 506 was 124 in Chem Phys, 127 in Cars, 127 in Biochem, and 128 in Psych Soc.
Okay.
And Mm. And for the 510, it was 126 in Chem Phys, 127 in Cars, 127 Biochem, and 130 in Psych Soc.
Got it. So let's see. Um, hmm. So okay, I guess I'll have it in your schedule like the week before your test to take an AMC test, but we can make a more informed decision by the time that comes around because prior to that, between now and then, you'll be doing two third-party full lengths, and the section that seems like that you need the most work in or did need the most work in was CP, and the blueprint tests have really good CP sections. So yeah, so I would just say continue doing like blueprint tests for this weekend and next weekend, and then after that will be the last weekend before your test. And that's when we can decide if it would be best to retake an AMC exam or not.
Yeah.
Like,
I took the week off for the week right before my test.
uh
I'll have more time as well.
oh, the week of like the 1st to the 6th, or
The
the week.
week from like the 6th to the, I
Okay,
don't know, 7th to the 13th. I don't know. Yeah.
the week of. Okay, okay. Yeah. So,
Eighth.
okay, okay. Got it. So, yeah, so take your blueprint uh test this weekend, either day, whichever day you want. Like, I guess tomorrow, if you want to do it like tomorrow, you can like, I guess, review it and stuff like on Sunday, or if you want tomorrow to be a day where you really iron out all of like the stuff that we learned, like doing UWorld uh um passages for like the electromagnetism. That one that you showed me, like I haven't seen the rest of the questions, but it seems like they'll ask you something about radioactive decay. It seems like they might ask you something about like a solenoid type of thing with the curl, like the rings or coils rather. Um, and it had some other stuff. So yeah, I would say so either tomorrow do more UWorld stuff for the magnetism, harmonics, buoyant force, all that stuff, circuits, all the stuff that we like talked about this week. Do a bunch of UWorld problems for that stuff. And then on Sunday, you could take your practice test. I think that would be better than taking the practice test tomorrow and then Sunday, like either reviewing it or something. So, yeah, what do you think about that?
Yeah, I like that. And I guess we could meet again like next week, same as this week. I think it was useful to meet every day.
Yeah, yeah, we could do
Mhm.
that. So I'll put you in for like 7, right?
Yeah.
So, got it. Okay. Anything else?
Nope.
All right, awesome. So, uh, good luck and have a good weekend, and I'll see you. Yeah, email me when you, yeah, with your score when you get it, and yeah, and then also like email me, I guess, like stuff that you want to go over for our sessions. But
Okay.
yeah, have a good weekend and good luck on your practice test, okay?
All right.
All
Bye.
right, take care. See ya.